Oh, there you go. That work? You want to mute yours?
I think I should. Oh, but it's hooked up to the TV. Okay, that's gonna be.
Okay, so go through here. Okay, it's fine. Sure. Oh. Okay, okay. Let me stop the sound. I muted me for. Sure.
All right, we are thrilled to have Courtney Paquette here giving a talk today. She's an expert in optimization, random matrix theory, and today she's going to talk about theory of momentum in SVD and how it can be used to how adaptive momentum can be used to accelerate training in LLMs. So thank you for coming.
Yeah. Oh, do we want to wait a moment? No, okay.
Go ahead.
Okay, all right. Sorry, there's a coffee spill in the room. So, yeah, so I want to talk today about some stuff I've been doing with stochastic momentum. I know people in here have looked at this. So, oops, maybe I'll just use this. No, okay, there it goes. All right, so what I'm going to talk about, I'll start with scaling laws. So scaling laws, right, it's just sort of another name that we've been calling things recently, which is that our loss function is somehow a function of iteration samples, number of parameters, number of neurons, etc. And why is this important? This is mostly important nowadays because we want to understand the interplay between iterations, sort of the actual algorithm, and also sort of the architecture that we're actually using. So that would be something like the number of parameters, for instance. Okay, and as many of you guys probably already in this room kind of already know, the main limitation nowadays is compute, not necessarily data. Um, and what we're seeing and what most people are trying to do with how these chat GPTs and things came about was that they were trying to answer a very simple problem, which is that for a given compute budget, infinite data, how do we allocate our resources? So how do we actually choose our learning rates, but also our parameters? Although please feel free to ask questions, especially probably at the later end. I'm gonna do something different. All right, so how do we do the scaling question? So let's mathematically formulate it. So here we're just minimizing some loss. I'm gonna let D be the number of parameters. And I'm going to let compute, which I'm going to measure in flops, be iterations times number of parameters. This is a fake computation. So just if everyone know, and I'll talk a little bit about this in practice, but let's go with this for right now. Okay, so what do we mean by a scaling question? Well, you might run, say, your favorite algorithm, say SGD, for T iterations across different Ds. You plot your loss as a function of flops, because you have this formula which relates iterations to parameters, and what you get are curves which kind of look like this. And this is curves which are, even on LLMs, they have this. Okay, and so the mathematical question is very simple. If you fix your number of flops, you have infinite data. How do you choose D so that you get your best loss? So this is an interplay between the algorithm and D and the actual architecture. So many of you have seen this plot before. So here you have your fixed flops. You're running your thing. You can see that if you choose D too small, you might run into some sort of stationarity idea, which is that the model size isn't big enough. So you get stuck at some value and you just can't do anything. And if you continue, you would just be wasteful in flops, right? You can also then increase to get more capacity in your model, say to 51,000, but now it costs more money, right? It costs more flops to do, so you can't run as long. And so you get stuck because of the optimization algorithm. And so the idea here is that there's a trade-off. There's some sort of Pareto frontier where there's the best D here. So I think I forget, let's say 12,000. Either that or 6,400, one of those two, right? And we do this for each of these flops and we get a curve, which we call the compute optimal curve. So that's what they talk about. And then the idea here is that if you wanted to extend your flops to something way, way larger, you can just use this curve to figure out your D, your optimal D. Okay. All right. So there was another big question that was out there, and I don't know the answer to this empirically. Okay. And there's reasons for this, which is that there's this evidence which says that nothing can actually beat SGD. So all your algorithms don't really matter. All algorithms give you the same exponent, and what you're doing is you're just optimizing constants. Okay? And why I will say this is really hard in practice to actually verify is because the actual exponents that you see are extremely small and you don't have a lot of data. So it's really hard to exactly say if you're actually beating something, okay, in practice, okay? But we can actually answer at least this question, maybe more in a controlled setting. So the idea again, how given fixed flops, how should you choose your parameter D so that you get the best loss? And then outscaling, or if you would like, what we were calling outscaling would mean that your D star as a function of flops to some exponent, you want this exponent to be better than SGD, provably better than SGD. Okay. So what do you do? So this, by the way, this was an adventure of mine for many years. Um, Elliot and I worked on momentum back in 2021, and I had to convince Elliot that this was an interesting thing to do. And then 4 years later, it started to become more interesting because people actually cared about it more. And now I think it's very interesting. So it started with nobody caring about it. So what's the thing? So people tend to use, at least in the theory group, use stochastic gradient descent. So that is you generate at each new data point in x t plus 1, and you update your algorithm just using that one sort of stochastic gradient, and you have a learning rate here. But in practice, nobody uses it ever. In fact, even if you might call SGD, they actually are probably running SGD with momentum. Like the actual built-in algorithm has momentum. So what is momentum? Some of you probably have seen this. Basically, the idea is that you should keep a history of your past gradients. So instead of just using, you can think of your gradient as being your current information, where you're just moving in direction of negative gradients, like just current. Whereas momentum is sort of remembering your past iterations. So where everything's coming from. So you keep this MT, which is some sort of moving average of your past gradients. Okay. And what I'm going to do is I'm going to have a stochastic gradient. I'm still going to use my current information, but I'm also going to update with sort of the past. So I'm going to do some sort of combination of my current gradient and the past gradient. Okay. And so I'm going to let beta 1, I wrote it maybe in a different way than you guys have seen before. The reason is I want to put this into something atom related. And atom has this EMA sort of thing going on here, so I'm putting it in there. So beta 1 is going to be my momentum parameter. Gamma is like my learning rate, and alpha T I'm going to call it the damping factor. Okay. And this is basically used everywhere. Any algorithm has momentum as part of it. Okay, so what the big question here is, first of all, why do we use this? Like, it's used in every algorithm. So what does it gain? What can you actually say gain? And then the longer term goal is actually, can you actually design new algorithms which sort of work at scale that are sort of in this framework? So how do you choose all these parameters properly? Is okay? So it's not quite the same. Most people sometimes don't have this. I'm adding this in because of a deterministic algorithm, which is going to be the basis of a lot of things. Is that right? Although you can go between this one and the one which also doesn't have this one here. Okay, it just affects this alpha here. Okay. All right, so if you go to deterministic optimization, so you don't have a stochastic gradient, you actually compute the full gradient. We know that in that setting, momentum results in you allowing to take larger learning rates and they're more stable. So you get larger learning rates, which are more stable. Moreover, if you are in sort of the strongly convex function, then we know that you can choose gamma, alpha, beta 1, and a determinant, the constant, so they're order one quantities, and you can show that gradient descent with momentum actually beats gradient descent. Okay. If you're in sort of just a pure convex, so non-strongly convex, not a quadratic, there's an algorithm out there that's just called Nesterov's acceleration. And it has this form. Again, it might look a little different. I put it into this form. So notice the beta 1 here is like a time-dependent beta 1. Okay. And that alpha t here is a time dependent also, but notice that there's one, you only get one constant. So you only get to choose this gamma tilde term. Okay. And I'll go through this a little more in depth. Okay. Later on. So why does this fail stochastic? Why don't we see this thing? So the biggest problem that we have is that with the theory has to do with stability. These algorithms are more aggressive. So they tend to take bigger steps. They tend to be way more aggressive in their path. So you get instability because you have stochasticity. And then what people tend to do in practice is they just fix the momentum to be a constant. So they'll just choose beta 1 to be like 0.9. Just that's it. Why 0.9? You guys are too young. Uh, but back in the day, there was a talk at Stanford. There was a class, and Andrew said you should use beta equal to 0.9. And 20 years later, we're still using 0.9, and nobody knows why. Yeah, yeah, yeah.
So like my overall question is what is known beyond acceleration about performance? Is if there is a gap in some case, or if in the deterministic case there shouldn't be, you can only accelerate.
Yeah. So for non-convex, fully like an actually non-convex, gradient descent is known to be optimal from the worst case complexity view of the thing. So like there exists a function for which you cannot improve from an information theoretic viewpoint. Like if you're only known gradients, if you're only given gradients, you can only get so much information from those gradients. And the optimal one is gradient descent. For convex, this algorithm is known to be optimal in the same sense that I said. Like if you only have gradient information from an information theoretic viewpoint, this algorithm is the best you can do. The same is for heavy ball.
Is it
Yeah.
best among deterministic algorithms or
Best are among, so there's among what they call first order. So ones which only use gradient information.
Gradient of the full risk or
Gradient over the full risk, yeah, but not it's not optimal if you're allowed to use Hessian information or things like the Hessian. Okay, then you can actually get a little bit faster than this. But if you're just allowed gradient information, this is the best you can do. Yeah.
are these like, you know, you're saying like
Yeah.
an existence proof, like information theoretically, you can find a
Yeah.
function that has this property where gradient descent can't be Are these like naturalistic or
Yeah.
kind of contrived?
So the non-convex one, I think is a little bit contrived, but also it's like a really broad class of things. So the ones for these two come from basically quadratics. So if you play around with some of the quadratic things, you can get that's sort of the bound that you have, and so that's where they come from. Okay. This algorithm is notoriously known to be completely not, how do I say this? It's the way these choices are chosen. So the way beta 1 and alpha are chosen is just from like an algebraic view. You like write down the things that you need and you just like set one term equal to 0 because you don't want to deal with it. And when you set it to be 0, this is what you pop out as like the choice there. So it's like the proof is totally non-intuitive and people don't really understand it even from that viewpoint. Okay, like it's just like the proof tells you this. Nesterov's still alive. You can ask him. People have, and he literally says there's no like reason. Like it's just an algebraic equation that makes these quantities happen. Okay. And I can kind of, I mean, okay, we'll go with that. Let's go with that. So what I was mostly interested in doing is, when you start to do stochastic things, and you want to do scaling, you need to understand how all these sort of hyperparameters depend on time and on model size. So on the whole T and D. So what we're interested in is doing this. We were working mostly with like some form of our alpha and beta. So our alpha we assumed had sort of like a D to some power plus 1 plus T to a power. Okay. And our beta also had some form like D to a power 1 plus T to a power. So we're just working with schedules, which are sort of polynomial. Okay. This is to make the math easier, but actually in the high dimensional one, you can show that the optimal ones look like this. You do like Laurent series. So you just write out Laurent series and you kind of show that like this is the best. This is the only term which matters. These 1 plus T powers matter. Okay. In terms of this framework also it captures everything that you want. So you see SGD, you see classical momentum. So by classical momentum here, I just mean everything is constant. It can depend, some of these you can depend on D, some don't, but in general, constant, no time dependent. It covers that Nesterov, if you were to make a stochastic version of it. It covers what is people call schedule free. So schedule free is actually with beta on this and kappa equal to 1. So why am I mentioning schedule free? Schedule free actually won one of the big algorithm competitions out there where they show that it actually is one of the more universal best algorithms across a variety of problems. It covers what people call accelerated SGD, which I will talk about, and then it's going to cover what I'm going to actually talk about today. Okay, so the goal again is how do you choose these hyperparameters in D and time so that you can actually beat SGD? Okay, everyone good? Okay, so I'm just gonna start with the parallel random features model. I think you guys know this. Okay, good. I don't have to worry. If not, please, please ask me. I know most of you have seen this, but what is the idea here? You have your data, X, it's embedded in RD by a random matrix, W. W, I'm going to assume, has entries which are normal distributed, 1 over D. My model I'm going to have is that it has J to the minus 2 row. Sorry, I changed this because I was using alpha for something else. And my target is also going to have power law distribution. And then I think most you guys have seen this style before. This K hat DWW transpose D is going to play a role. D is going to be some diagonal matrix with the power law on it. Okay. And again, what we said, our interest is just to find these exponents. People in this room have worked on this problem using this model. It's a model which generates this picture here. It's related to things which people call source and capacity and all sorts of stuff. So this model is pretty well known. Okay, so let's just talk about the classic one because this is the one that people do. Classic just means let's assume all of our hyperparameters are constant. So gamma is just D to a power. That's our learning rate. Our alpha is just d to a power, and our beta one is literally constant, like not independent of d. Like I mean like the 0.9 kind of thing. Okay. Intuitively, not even on the random features model, we should expect momentum to do nothing. Okay, why? If you actually look at MT with beta constant, okay, you just solve this expression. If you solve this expression, you get NT as some sort of exponential decay in the gradients of the path. Okay, but for stochastic optimization in particular, for your gradients don't move very much. So you're killing off your path gradients exponentially fast, and they're not moving a lot in between. So you're only really getting a little snippet of your current gradients, right? And those gradients aren't moving enough in the time frame that you're killing everything off. So you're basically getting the exact same gradient as this one here. And so what you're just doing is you're just rescaling the learning rate. So what 0.9 is in essence doing is just rescaling the learning rate so that you can take a larger learning rate. Right? It's taking one where you can take it so you get a learning rate of SGD would just be gamma plus alpha now instead. That's sort of the idea. And in fact, you do see this. So you can actually do this on real data. This is an LSTM. You can use SGD. You can map SGD learning rate to this momentum via this formula. And what you see is that the two are actually really close. SGDs are the solid lines. These different momentum ones just all lie on top of the SGD. So this is like totally normal. Like we expect this to happen. So what the 0.9 is actually doing in some sense is just like letting you take a larger learning rate, one, and two, it's doing a little bit of averaging. So it's giving you a little bit of extra averaging in your gradient to reduce variance. That's how you should think about it. That's what's going on. And that's fully general. Okay. So let's look at what we know is optimal, which is Nestorov's acceleration and what happens here. So with Nestorov's acceleration, we know now is that if we want momentum to do something interesting, we need to have it on a time frame, a momentum that's keeping the history a long history. So the natural one to try is the one that Nesterov came up with, which is, if you think about beta 1 here, it's like t minus 2 over t plus 3, right? So using some sort of really long history of your momentum. Why is this? Well, the idea was, what I think is what was going on with Nesterov is that on this time frame for convex problems, your gradients actually move. Like they have a chance to actually move and do something interesting. And so let's try that. So if we use the long momentum and we choose this alpha of t, you see here, I'm just plugging in directly into Nesterov. There's a problem with stochasticity now. So deterministic, if like you've computed the full gradient, this is a fine algorithm. It has no problems. It's provably fine, right? But in stochastic, it runs into an issue, and you can kind of even see it. So if you take some gradient and you just add the full gradient plus some noise, you could have this be variance, epsilon with some variance, which would say order 1. What happens when you unravel this, because you have a long history now, it accumulates. It accumulates and it's bad accumulation. The bad accumulation gets hit all in this MT and it just stays there. So now you have sort of orders of magnitude wrong on the noise that your stochastic gradients are seeing. You have a GT plus 1 here, which is like just one gradient. And then you have a history, which is accumulating a bunch of gradient, okay, which is giving you some problems. These two are now not on the same order. And the issue is that you only have one hyperparameter to choose. So that hits both of these because of the way that Nesterov is set up. And you can't do it. So you would choose a hyperparameter to do it, but then you're going to kill off one of these two terms. And the result of that is that you get instability. So even if you were to choose it so that you're controlling all the noise, you can actually provably show that there is no choice of gamma tilde for which you actually gain stability on the power law random features model. And this was proven. They didn't quite do it on the power law. It was proven by Francis Bach. They did it on the source and capacity, but it's the same sort of setup. So we should think of it. That. And you can see this. You can run this and you can see it really doesn't hold. Okay. And this is true. So why does it matter? So this is on real LLMs using Atom. So just to give you a sense of this, Nesterov needs both these two terms. It needs the gradient term and it needs the momentum term. You cannot have one, you can't kill off one and have it be a stable algorithm. It just doesn't work. It needs the two, okay? And you can kind of see things like this. So for various reasons with Atom, you can play around with different things. It actually does worse if you kill off various terms than just doing normal Atom. Okay, with the log time momentum. So using a beta 1, which has this 1 over t, okay? If you try to do just pure Nesterov, which is this one, you see it diverges. So even with real data LLMs, like Nesterov is like too aggressive of an idea, okay? And you sort of need both of these. Like you can't get away with just a gradient and you can't just get away with a momentum. If you want to do the long time, like long time for the beta 1. Make sense? A little bit? Okay. So what's the natural thing to do? The natural thing to do is to damp your momentum. So to add in a momentum term, a damping term to your momentum, which is distinct from gamma. So you don't have just one hyperparameter, which is controlling both of these two terms. You want two of them at least. And you want to choose it in some sense so that these two are kind of on the same order. Okay? That would be the idea here. So you do this, you use your long momentum. So you're still doing this 1 plus t to the minus 1 behavior. You have your learning rate. I'm just assuming you is roughly like 1 over the trace. And then you get to choose your alpha of t. So one way of choosing your alpha of t is to choose it so that it's small, so that it looks like a 1 over d. Okay? So it's d sort of dependent. But the problem with doing something like this is, which by the way, there's a related algorithm related to this, is that you need, when t is smaller than d, this is basically negligible. And you're just doing gradient SGD. So, and you kind of can see this, this is this green curve here. You see that like it's negligible and then after t is equal to d, you see an acceleration. But it requires d steps before you see anything because this thing is being killed so fast, at least at the beginning with the 1 over d, it just, you don't see it. So you need 1 over d for this to even start to appear. Okay? So
And the annealing and time of that is to kill the noise. It was.
yeah, it's to kill. So in the random features, it's a little bit hard. It's not really, it is the noise. It's like the variance from the
From the W.
Yeah, exactly. Exactly. You have to kill it and it's being sort of, it has itself a power law sort of decay going on. And the 1 over d is, it turns out exactly what you need to make it stable. If you if you've wanted that to be a constant, if you want a constant here, then you need the 1 over d. But of course the issue is that it has this weird effect, which is that for t less than d, you just don't do anything for, which by the way is a problem. This is actually a big problem for when you do compute optimality, because you do compute optimality, you run your iterations t on the order of d. So you would never see any acceleration from this type of algorithm. So it's actually an important fact that you would not see this if you were to say run chinchilla scaling. All right, am I going too fast, everyone? Okay. So what you actually can do is you can actually, in some sense, you don't need exactly 1 over d. The 1 over d was needed so that at sort of the end, you were stable. You need the 1 over d so that, once you run, you just reach a plateau and you stay at a plateau. So what you can do is you can sort of decrease that and you can choose it a time dependent thing, which is out with this thing here, 1 plus t to now 1 minus 1 over 2 rho. And the rho here has to do with the exponent on the data. And this happens to exactly match edges of stability that you might have. So what do I mean by that? So if you look at alpha t, where you let it be, oops, sorry, this should be 1 plus t. So it's like d to a minus power. And you run this for different powers. When your power is too big, it will, or too small, it will diverge. So run and then it will diverge, run and diverge, etc. If you choose it too large, which it means that you're being more stable, then it gets worse performance. Okay. Same thing here. If you choose 1 plus t to the 1 minus kappa, you change your kappa. You choose your kappa to be too aggressive, it will go and then diverge. If it's not as aggressive, you get slightly worse, eventually becoming SGD. What this one is exactly the thing that maps out the divergence. So as it goes, it diverges. This is the rate for which it stays and hugs the system all the way through. So it's like really on the verge of the instability for this.
So if you ran this algorithm for infinite steps, it would diverge, but you're gonna cut it off?
No, this will actually converge. Why? Because if you plug in, so you plug in the time that it takes to reach this, like where you're stable, it actually gives you 1 over d. So it like maps out exactly what you need to reach at the time that you're actually at the stable point. So it will not diverge for an all time, but it allows you to take larger steps initially. That's kind of the idea behind it. Yeah.
Raw is there is data or is an arbitrary?
So rho is, so it's the power law exponent on the data. Yeah. Not on the targets. So that's actually really nice because it's on the exponent on the data and not the targets, which you actually sort of have an idea, at least kind of what it should look like. Or at least there's hope for it in LLMs. This really does fix the problem. So the orange curve is indeed the data decay sort of idea where you just have a time dependent thing. You get all the way from time 1, basically an acceleration behavior. So it's quite nice. Just to say, because you guys probably want to know how to prove this. Okay, so you can't. How do you do it? So for momentum, what you want to do is you want to have 3 sort of, well, there's 3 summary statistics which kind of matter. So you first you compute the eigenvalue and eigenvector pairs, at least this is what we did. I'm working with a continuous version of the momentum. Oops, sorry, this should be M. Continuous version of this operation of the update parameters here. And so your rho is really like theta minus theta star if you want. Okay. Your C is the momentum and your chi will be the cross term. So you have these 3 terms, and then you can recover the loss by just summing up the rows. Okay. So what you get is that for each eigenvalue eigenvector pair, you get a 3x3 system of linear ODEs, which is sort of nice. The only thing here, and they're just coupled, but they're only coupled via very lightly through this term right here, which is sort of just the loss itself. Okay. So just to say, with SGD, you would just have rho. And so your A is an R. And so you can solve that because it's just a 1-dimensional linear ODE system. For momentum, it's way harder, but you still have Duhamel's principle. So you can still solve it, sort of. Okay, sort of here means there is a reduction that helps. So this comes from the high dimensional regime. So some of you might know this, but basically, if your gamma in high dimensional regime, the learning rates will depend like on 1 over d. And it's true for kind of all these parameters, they're like 1 over D. So what happens here in this A formulation, you'll get products of things. So you'll get like gamma squared, gamma times alpha. Like you'll have a gamma plus like a gamma times an alpha, or a alpha plus an alpha squared or something like that. Well, in the high dimensional regime, you can actually kill off all of the square terms. So anything which has a product of those can actually go away, because as long as you leave sort of the largest order on each of them. So this one you have to leave because it's the largest order, but this one you can kill off.
If your features are trace class, then you don't do that.
So it still works. The only thing it really affects, which I still can't really explain, is it only affects sort of the constant that you need for like true upper bounds to say you need this learning rate to be less than this value. It doesn't affect like the asymptotic relations that you get.
So as a heuristic, when you're looking at this 3 by 3 thing, throwing away quadratic and higher
Yes,
terms and hyperparameters.
just works. You can kind of do it from an ODE perspective where you take like, you have to decompose this A into a couple of terms and then try to show that like the part which has like the quadratics and these things don't actually matter. But yeah, it's not the same as SGD, because I know with the SGD you'll have like, you might get like a gamma squared times a lambda squared. You don't get that here. You literally have to kill off all the terms which are like gamma times alpha, and it still works as a tonic. The only reason I know this is, or would guess that that's true, because it's exactly like you, it should be trace class, is because of the high dimensional one, which killed it and it gave, and then you just try it and it still works. So not sure. Not sure why. And it's not from the eigenvalue, so it's not like it gets multiplied by the square of the eigenvalue. It just doesn't appear in the asymptotic. So once you have this, you can write down actually a Voltaire equation. You have a convolution Voltaire equation. It's a little bit more complicated. Okay, it's a lot more complicated. Those ODs, like linear 3 by 3, which seems like they should be easy, are actually really quite hard. And you can solve it. You have this, and you can replace it with a deterministic equivalent. Everything else is the same, and you have sort of a deterministic ODE or a deterministic Voltaire equation, which describes the behavior, and it just depends on those eigenvalues of this K hat matrix, so this DWW transpose. And it's just a really good, again, it's a good predictor for the behavior of these things. Okay. And like I said, you can do this with or without dropping the products, and they're still all match. Okay. And then what you do is you can estimate your loss. So you can show that your loss is just really some constant times F plus K on both sides. The only difference here is what is this 1 over for gamma hat here. For Dana and SGD, it's just your gamma. For SGDM, it's like gamma plus alpha for the relationship. Okay. And the same sort of stability conditions hold. And this is actually where you figure out what your alpha should be, is because of this problem right here. So you need your kernel to be an L1 to be less than 1. Mostly you just need your kernel to be summable if you really want. The less than 1 is sort of not important. And the nicest part about all of this actually is that all these weird sort of learning rate stuff with time-dependent momentum don't actually change very much. What they do is they just change sort of your time that you evaluate these quantities at. So I'm going to break up my forcing function into 3 terms, okay? And those 3 terms are based off, they have a simple formula, so they're just t to a power d to a power to show explicitly. What you're interested in is understanding the eigenvalue behavior of this DWW transpose matrix. You can write down the deterministic equation and you'll get a formula that looks like this. This is the red The gray is a simulation of that random matrix. And you see there's like different sort of behaviors in the spectrum. So you see the point masses. The point masses will give you FPP. They sort of smooth out. That gives you sort of the misalignment. That's the result of your W causing some sort of noise to start to appear. And then there's a point mass, which has to do with your irreducible loss. Right? You can do the same thing with K, but it turns out the only thing which actually matters are the spikes here. And kappa here, or this K is really related to the actual SGD algorithm. So what this means is that depending on your rho and beta, you have just 4 phases where your loss will only sort of one of these components will dominate. So in phase 1, you only have FPP and F0. Okay. Phase 2, you'll have FPP, FAC, F0. So in that phase. 3, 4, you have different components of these things dominate. Okay. Then to go between SGD and say momentum stuff, the time change is given by this formula here. And how you choose your alpha, then it's just a matter of saying you would prefer to make this thing matter more than this quantity because that's just SGD. So you want this thing to matter more while still being stable, while still making sure that the norm of the kernel is less than 1. That's like the entire game that you have to play. And there is a choice of alpha for which that happens. And that's exactly the 1 minus 1/2 rho.
So it's like anything that decays more slowly, like K and decay would diverge.
Yeah, exactly. That's why you get these, that's why at the beginning, these pictures where you had like this, it's exactly mapping this. Like you would actually diverge. This is like the right at the edge for which you still have the kernel is summable. And like, I mean, it's at the edge of making the kernel summable, basically. And that ends up being, and then it just so happens that with the kernel being summable, that choice for alpha makes this term dominate over gamma t. Otherwise, if it was summable, you needed an alpha super small, and this still was the dominant term, you wouldn't see an acceleration. So it just so happens that that one is can be done. Make sense? The idea? Cool. And then like I said, it's just a time change. So to get your loss, you just plug in that time change. So it's actually quite nice overall. There's only a time change. Again, what you see, you'll see something like this, like so phase 2, right? You'll have 3 components for these Dana constant, Dana decay, and you'll still see the same components, but they'll just be at steeper slopes because of the actual different time. And you get acceleration everywhere where 2 rho is bigger than 1. It's unclear what happens when 2 rho is less than 1. I don't know what happened. So it's still unclear if you can actually even get any kind of thing. This is why language we think is kind of nice because it probably kind of lives more up there than down. But that's just language. Vision might actually live more down below. Another thing this does is that it extrapolates really nicely. So maybe I'll do this on the second slide, but basically this just shows you exactly what is the effect of Dana decaying versus SGD. So if you look at how it changes from here to this line, what you see is you get this factor 2 minus kappa. And so you gain sort of almost like a square. So why is the 2, so you gain 2 minus kappa. The 2 is important because this is exactly the gain that you get from Nesterov's acceleration versus gradient descent. So this is in some sense doing some sort of extrapolation between it. And you can see where it hits on all these terms. If you wanted to do ridge regression, it just follows, you just drop the KPP term, replace it with FBP everywhere. So you can also get the ridge regression values from this too. Same thing with if you wanted to get the like with source and capacity, you just drop the FAC, so the grade term everywhere. And you have the same rates. So it doesn't change anything. So this is like what I was saying, you can actually now sort of map, like you have D to a power and 1 minus kappa, the effect of kappa and D. Sorry, this is kappa, this is kappa 2 to your power on D. And you can see the data and plot sort of what is like the best rate. And you can plot Dana decay actually gives you the best one over all of these. As you change, as you make different kappas pairs, you get worse. Dana constant is here. Schedule free is here. It's on the edge between just being SGD, and in fact basically is. And this is a line of stability, which you can plot. And basically what happens is as you make full batch, as you increase your batch, this line is getting closer and closer so that it encompasses Nesterov, which is like 0, 0. It's like pure constant term. So this is like an extrapolate, like I said, it really is just extrapolating with Nesterov to make it work in the stochastic setting. And you're choosing sort of the learning rate to just be exactly what you need for stability. Any questions before I go totally off book? No math whatsoever. Okay, yeah.
Is this, I was wondering, so in your model, is the only noise that's generated in SGD coming from the like finite model size? Like
Yeah.
if there was just some irreducible Bayes there, like some.
Yeah.
Does
Yeah.
that change the picture?
It does, but it does and it doesn't. So you can, the problem is that if you wanted to get the scaling law, then you need at least that your noise go down to 0. Otherwise you won't get the scaling behavior.
Well, you could, right, I guess L minus L0 or something.
Yeah, you could do L minus L0, exactly. But then you're like killing that off anyway, so you might as well just use it that's like not there. So I think that's maybe a problem with the model more.
Well, I guess that might, so even though you have an L0 like additive contribution, the question I guess is like, what if the coefficient in front of the SGD noise doesn't decay with the.
Yeah, so this is okay, I'm gonna show you. I think it still works. The question is, what is kappa? I don't know if it's like 1/2 rho in that case. It might be dependent on the noise. Like if your noise had a exponent, power law exponent going down, it might affect it. And I'll show you that because that's why there's something that was interesting about when you do this on LLMs. Okay, so maybe just to start, we were super interested in trying to make this practical. We are not empirical people, okay? So I'm going to do this from like, we tried to make a science out of, out of what people did. So we tried to make this practical. So the natural one to do is, this is not like the practical algorithm. The natural one is to make an atom version of this for LLMs. So you still have a damping factor. The question is, what is kappa, but now for actual LLMs? And how important are all these quantities in making this thing work? Okay, so I'll try to do this. So the way we did this is we use chinchilla scaling. So C is my compute, N is my data, D is my model size, and P is my non-embedding parameters. Hopefully you guys all follow this. You probably switch these two, but it's okay because in compute it will 6ND. So technically the N is actually this formula, if you've ever seen this. It's not quite N in the formula, but this is what they actually use for chinchilla. And then we're going to use a scaling ladder, which is from the DLocal scaling ladder group. So DLocal scales proportionally attention heads and layers. So its width and depth are scaling proportionally to each other by 3/4. There's 3/4 of them. Hey, and then they fix the head dimension, which is probably a problem because this would be making your value matrices and whatever your key and query matrices actually get skinnier as you go out, but they're probably not so bad here. because we're not super large, and then these things also scale, okay, all together. So what does this look like? This is an atom version of what I just did, okay? So you have beta 1 is your MT is your momentum. Beta 2 is dealing with your second moment. You're going to add an alpha, which is your damp Nesterov scaling, and you have to deal with weight decay. So you have to put in weight decay in here. My weight decay is independent, so it doesn't have the learning rate. It's not how you don't actually have it for the it doesn't have the learning rate. So if you code this, you have to divide. I'm sorry, everyone. I didn't make weight decay wrong. It really is wrong. Okay, so what you can show, which is crazy, is that for your damping parameter, your kappa is roughly 0.85, and it works, and your alpha tilde, your constant, is just 1. So this is with a fixed batch of 32, so I'm not changing my batch. What you show is that by doing this sort of thing, you actually get 40% compute efficiency gains just by choosing this correctly. And it works better as you scale up. So as you scale it, it gets better. Muon has a problem, but Muon has a problem because of batch. Batch is relatively small here. The other thing you can try and do is you can think of this as being fixed, and you try to run longer in time, run longer in scale, and then try to find the best constant. And if you do that and then try to fit a line, you actually recover this formula 1 plus t to the 1 minus kappa, weirdly enough. So it's kind of crazy.
So
Yeah.
how did you determine this kappa? So is it like this, you did search and then you asked, like, when does it become unstable, or?
So we searched, and what we did is we just tried it. So we tried, okay. So we saw, I didn't show a picture of this, but on LSTMs with C4 data, so this is with fine web data, instead, it was roughly 0. We ran it and we waited until it diverged and then found it from that. And it was roughly between 0.75 and 0.9. Even on fine web, it's exactly the same. So we sort of started with that range, knowing a priori from LSTMs that was good. Then my student Damian was like, let's just test this. So we found, I'll show a picture of what kappa is, but we found that if you run longer in time, like, you just suppose this were constant, run longer in time, run longer in like scale up models, go past chinchilla, then try to fit to this form, you get the exponent 0.85 or 0.853, whatever. So like it somehow is like matching the correct rate. Okay, why 0.85? So there's actually another paper that just came out on this, which is Surya Ganguly's paper. Elliot also thinks it's related to this. The 0.85 might be related to this entropy in tokens. So it goes to your question, Blake. That's probably exactly what that quantity is. So there's an entropy computation that you can compute, which is like you start with a context length. You look at what's the entropy of going to the context length plus 1. You can compute it, and it decays like the context length raised to this exponent. And Surya actually just fit it and saw that this was one of their exponents that they used to try and fit that line. They didn't call it, but it has a name. It's called the Hilbert exponent. It's actually a well-known exponent in language modeling. And it might be related probably to gradient noise. Like this might be the gradient noise exponent.
But it's just inherited from some like cross entropy or something.
Exactly. It's probably inherited from, so Elliot thinks it's inherited from the language. I mean, the series basically shows this, that it's somehow relating to the scaling exponent. Elliot thinks it's related to the stochastic gradient noise term, which might be decaying like some power to the 0.85.
But you expect something different in like vision transfer.
Exactly. Vision for sure. Vision will definitely probably have a different exon. But the weirdest part about this is it didn't really depend on the the data set. Like C4 is like a different data set. It basically has the same exponent. So I don't know if it must be like intrinsic to language. The vision is probably something different. Sorry, I'm probably going over. I'll skip all of this, but basically this is about hyperparameters. So if you're interested in this, but this is stuff you might be absolutely interested in. So we were trying to be very systematic. We're trying to be scientists about our power law stuff because most people aren't very good about it. Okay, so there's a lot of guesses of how your law should look like. If you try and just do a single, so what we did is we fit an A, so the A is sort of universal across all of them. If you fit just a single power law, you get worse performance. If you fit two power laws, you get better matching of the behavior. And this is actually predicted by your random features model. Your random feature model says you should have two compute exponents, and it's actually a better fit than a single one. But they give you totally different exponent values. So you have to be a little bit careful here, but this is definitely a better fit overall. It's kind of fun to do. The second thing is there's like a bunch of formulas for compute out there. You can actually test the different compute formulas. So there's Kaplan, Chinchilla, DeepSeek has their own. If you look at, you fit to the two power law, then you look at do a different compute, plot the residuals of how good you're off by. It's Kaplan and DeepSeek have like this very distinctive structure, which suggests that that's not good. Like that's the wrong formulas for compute. So that Chinchilla doesn't seem to have it, which seems to have a better function for compute. Okay.
Something like the vocabulary size is fixed or something. And there's a regime where eventually, like, if you keep going wider and deeper, you're dominated by the body.
Exactly. So eventually these two, they all are in the limit, have the same formulas for compute. But like at a finite time for horizon, they're different, and somehow these have like structured residuals. So we're not statisticians, but we assume that that's a bad thing to happen. Don't you want this? I don't know, maybe you guys are better at that, but that seems bad. I don't know if anyone has studied this, but we tried. We also ran it, of course, to Chinchilla Optimal. So we were running it on the Chinchilla Optimal theme. So that might be why this is better, but still it's kind of unusual. Those compute formulas don't hold. I'm probably running out of time. Sorry, guys. But you asked about kappa. Kappa is super important. So if your choice is kappa, if you're a little bit off from it, so like this is 0.75 to 0.9, what you can see is like 0.85 is like pretty good. And if you're at 0.75, you're at like maybe only 20% better than Adam, whereas at 0.85, you're like 40%. So like the choice of this kappa is super important. The other thing which is important to note is that if you choose kappa is equal to 1, you recover Adam, and indeed you do that here. So like you somehow are matching theory with what you expect for kappa behavior. The other weird thing that you should do has to do with weight decay. Weight decay should also be on a log scale, so it should also have a 1/t behavior to it. Why? Because everything else has a 1/t, so your parameter should also be t minus decaying like t to some power. This just makes sense, so you should put weight decay also to be like that. We did like a warm-up weight decay, and this has to do more with Adam than anything else. So this is this idea that you want large weight decay at the very beginning, and then you want to decrease it down to be like 1/t by the end. The 10 is arbitrary. Okay. Omega turns out to be very, very consistent as like there's one answer, it's constant, it's like 4. Like you don't have to do much to it. But you really do want a 1/t weight decay. It just doesn't work very well. This just shows you if you did a straight up 1/t, you start off really bad and then you actually get better. over time, things like that. So I won't go into it. Maybe I'll end here. I'll just say something about learning rate. Learning rates are also problematic. So what we did was try to be very systematic about how we chose the scaling. We couldn't use things like mu-p scaling because we didn't know what it was. So you have to actually search. So we started with a coarse grid, then we did a finer grid, and then once you have the finer grid, we collected the top 5 learning rates. We weighted each of the learning rates based off of their loss value that they got, and then fit it to a power law of this form, which we found to be the better one to fit for. And if you do that, it gives pretty good predictions. So you're weighting, and then you can top 5 your weight, and then you can predict out the behavior as you go further out. It gave pretty good. This is just maybe to point out how the this one learning rate will change between Atom and A-Dana. The Atom one, you can just imagine Atom doesn't have this extra gradient. So at like initialization, A-Dana has a gradient and momentum, which means it's twice as large as Atom, which means that you should expect a smaller learning rate. And indeed, you do get a smaller learning rate. It's like 1/10 Atom. But you can basically take Atom. So it's kind of fun. And yeah, it works for batch. You can do larger batches and you get improvement. A-Dana actually eventually beats even muon at really large batches. You would never do this for this batch is way too big. 512 batches, way too big for this scale. This is way too, you wouldn't do this. But if there's a question about how does batch affect everything. If you believe in sort of the gradient noise view of the world, that this constant is really from the gradient noise, it shouldn't disappear really as you increase batch, but you do need to adjust your alpha quantity a little bit. And you'll have to adjust it. Why was I doing 0.5 minus kappa? The kappa is coming because there's a batch here, so it pulls out. That's where you get 0.5 has to do with atom scaling batch, which is off by a 0.5. So we were doing that. It also, there's a reason to suggest from the parallel random featured model that your kappa actually decreases also as batch goes up, because it's like you're going down to full batch. So you should get a little bit of, so you can do that and it works. It's beautiful. It's kind of fun. Anyway, we were playing around with batch, so I'll end here because I know I'm over. So sorry. And that's these 2 papers. Yeah, the last one is like the really empirical one. So yeah, thank you.
Any questions?
Yeah.
The shape of at least most of the schedules you presented do not depend on the total training time. So there are kind of anytime schedules.
Yeah.
Do you think using that information could change the exponent in your setting? Or?
So you can, so there's a way to, yeah, so it's a good point. So we tested this a little bit. So what you could do here, so the 1 is there for reasons just to make for the Nesterov. So you could put kappa is equal to 0 and then train your alpha to be like last number of iterations dependent kind of view. And we did that. That's actually what this atomamic one is. Atomamics actually has this. That's what they assume. And over time, it doesn't scale properly. So it somehow, yeah, like you can fit it and it just doesn't scale. It degenerates back into atom very easily. Another to your point is we tried to extend beyond just like the chinchilla. So to test if it should be like time dependent or not, like iteration dependent. So you can run it way longer than chinchilla and see how good it was. And it was doing fine, even way past chinchilla. So I don't know. I don't know if it's not conclusive, but yeah. Somehow if you sort of fix it, make it a constant. I mean, what would happen is eventually it would blow up after that time. But it doesn't work very well at scale. It didn't scale properly. So I don't know. Maybe we did our scaling wrong. It's really hard to scale. Let's just say that. It's like exceptionally hard to do all these power law fits because everything's extremely noisy. So yeah, cool. Other question? Oh, sorry. You guys have others?
Do you expect that the batch size might need to grow? Change?
Oh, 100%. But batch scaling is another whole problem. It, I mean, what all this is, I mean, certainly how batch scales is for muon and atom are different. They're just different batch scaling. I think in the regime that academics can actually how do I say run experiments at, the batch is basically fixed. You don't run 512 batch at the small scales. Atom works way better with smaller batch scale. And like we were running from 45 to 2.6 billion. I think it like doubles like what people say for batch scaling. It would just be double. So it's not like you're huge scaling your batch over that regime over the 45 to 2.6 billion.
So you mentioned a comparison to muon, but
Yeah.
there's other, I guess, preconditioned optimizers that have like a moving average kind of
Yeah.
like moment, like so there's like shampoo.
Yeah.
Would a time varying
It should work. It's the point I think that people were having is that you should always have done we've always been moving towards it. If you looked at what the best beta 1 has been over the last few years, it's been getting closer and closer to 1. So it was like 0, I mean I said 0.9, but it got to like 0.95 and then it was like 0.99 was it for a little while, and it was just getting closer to 1. The problem was that if you choose the 1 minus 1 over t, it's an unstable algorithm. So it's like too aggressive. So you have to fix it some way in a way that scales properly. I think that's maybe the big statement to be made. The other statement, which I think you guys were, do you guys have an extra gradient? Do you have two terms?
So we've tried it both ways, but we were doing this like not an anytime algorithm, I guess.
Okay.
So it was sort of like the optimal control problem is you get capital T steps.
Okay.
And then what's the
Okay.
optimal like beta of T curve and eta of T curve?
I see.
Like,
Okay.
you could add 3, you could have the alpha and the.
I see.
gamma.
Okay. Because it was really important. Like if you don't have one, then it like blows up. Like at least in here, these blow up. So you need both terms to survive.
Yeah, so in our horizon aware, I guess, version of this, it seemed like the qualitative scaling was similar. Whether
Yeah.
it had- And so, yeah, so like you tell me I'm gonna do capital T steps. That may not be an algorithm that would converge for any little t bigger than capital T.
Gotcha.
But-
Okay.
But it gives you.
I see. I see. So it doesn't guarantee after either.
Yeah.
Okay. Yeah. So you can do stuff like that, but then you're not guaranteeing, yeah, that it works converging after. Okay. Yeah. But I see. Okay.
So then there's just a question, yeah, so like you say I have a horizon of capital T things,
Yeah.
optimize everything, and then like what's the scaling of capital T?
Yeah.
But like, in some sense, people do these like horizon aware learning rate schedules, like these cosine things.
Yeah.
and these other-
Yeah. No, you still have to do that. So here you have to do a horizon because Atom has a problem.
Yeah,
Just Atom itself, just because of the stupid moving average with the MT and
like the scale just,
the scale grows. So this is like growing, and so you have to decrease it by some amount from the learning rate because this is just growing no matter what. So I mean
I've always felt like that's kind of a defect. Like, did you guys try just like pure momentum on these models? Do you really need Atom? Or?
I don't know. I mean, I know for vision, like you can get away with just SGD plus M, like it's like now it works pretty good. But they say that SGD is unstable. And I'm not sure why it's unstable. And there's that paper which says that it works just as well with SGD. But I don't know. I'm not sure. It probably works just as well if if in small batch for sure. But larger batch, I'm not sure. So yeah, it's kind of fun. I mean, I would love to explore this more. This exponent is super weird and it's so close to like what is this token exponent entropy thing. I'm not I think it'd be really cool.
Yeah, there was a question I had when I was, so the serious paper, I guess, so like, in some sense, if you quantify all the entropies or something, it should
Yeah.
get like some bound, maybe.
Yeah.
And there's questions about how good different optimization algorithms are at achieving that.
Yeah. Yeah, I guess we were surprised because we had done it and we had seen that the same exponent and had figured out it was this entropy exponent and saw serious paper and they were using it. We're like, okay, maybe there's actually a connection to what's going, like, I don't know. That there's something about gradient. I think this is about gradient noise. Like gradient noise is this effect. And it's why all data language sets have exactly the same exponent, it seems like.
That's consistent with your finding that like if you make batch size huge or something, you're getting a different measurement for it.
Yeah. Yeah. So yeah, I mean, the thing is we didn't do a huge amount of batch size scaling stuff because batch size is so expensive. I mean, okay, just fixed batch is an expensive thing. This is like 14 GPU years or something like of runs and stuff. So like you do it with a different batch, it's the same. I mean, it's another 14 GPU years you have to waste, and we don't have a lot of it. So we use up most of it to do these plots. So yeah. Are you guys interested in the momentum stuff now?
We're trying, yeah, so even in this setting.
Yeah.
Horizon aware optimal SGD.
Yeah.
And you get some capital T's coming. Or the horizon aware optimal momentum, at least from the numerics we've done,
Yeah.
like it beats it, but we don't know how to calculate that exponent.
Yeah, so this is I don't know how like I felt really bad. I gave this problem to my grad student and that ODE, even when you assume linear time, is extremely annoying to solve. But the trick with any ones which had like if you had like I said, if you had gamma times alpha or something like that, it just kill it. Just drop it and see if it works. I don't know why. I only know why from the high dimensional version why it works, but I don't know why it works here, really. Like it affects certainly like the constant, but it doesn't seem to affect the asymptotic. So
The issues that the schedules that we get are kind of
They're weird, yeah, so it's
They're like-
not just a power.
pretty weird.
Yeah, like the data goes down for a little bit and then it goes back from one, like near the end of.
yeah.
As little t goes to capital T.
That would make sense. So there's some weird, yeah, like no, the scale, even like SGD, it's not obvious. The scale should go up, I think, and go back down again for the optimal schedules and things. It's not really obvious what to do. No, that's cool though.
What our hope is like to try to, I don't know, say how, what's the optimal curve, the optimal shape of these schedules look like as a function of like the source capacity, kind of structural properties of the.
Yeah.
the learning problem.
No, that would make sense. Are you seeing any kind of?
Yeah, so I mean, for SGD, we can do this, and so it looks kind of like looks sort of like cosine, it's like a polynomial schedule,
Okay.
but with an exponent on the polynomial that's related to the problem exponents.
Okay. So similar to like alpha then, I guess, a little bit, like there's like.
Yeah.
Yeah, okay,
exactly.
okay.
In some regime, or it could be some.
Or it's more
something
Or it
like
could be
USD.
flat, right? Yeah, some of them are flat and then they go down, right? Yeah, that's the
Exactly.
normal
that's more
one.
like the bias stuff.
Yeah.
Yeah, that's right. The prefactor may depend in one regime on the feature exponents, but not the. Not the, yeah.
So it would just be the row.
Yeah, exactly. The shape of the schedule only depends on both.
I mean, that's good because
Yeah.
it depends on your target. It's a problem, like it just doesn't extend very well. Like, I don't know. Like it doesn't make as much sense for LLM. So you can't just like test it and try it on an LLM because there's no such thing as the target. So it's a little bit harder. At least with here you can test them. Yeah, no, I was that's cool. That's very cool. Yeah. I I just this one is known. Okay. This one is known to be optimal for convex. There's 1/1 plus t. I mean, there's different versions of it, like 2/t3 plus t, but it's roughly that. They all look the same. And you can show it because like it's like basically if you have like an analytic learning rate schedule, momentum schedule, then you just like express it as this Laurent series and then solve it, and then you see that this is roughly the one that you need. Just go with it.
Sure, classic paper that there were
That-
papers to discuss
Ah,
this stuff or.
um, no, they're so, it's so, okay, like, when I mean that Nesterov did like a terrible job of explaining this, I mean, truly, this is like the worst paper you'll ever read. First of all, it's in Russian. Okay, maybe I should stop recording. Okay, I'm gonna stop recording. Let me, got it? Okay, cool.